Okay, so we're going to finish up here and start by talking about active noise cancellation. And essentially, this is used in combination with passive silencers to capitalize on the advantages of both approaches. So active noise cancellation are very good at controlling a lot of low frequency noise or provide a lot of attenuation for low frequency energy. So you can kind of think of the active noise cancellation in like Bose headphones. You know, it reduces a lot. It can use some filtering techniques to reduce low frequency noise. So one example, an easy example, is like a high pass filter. And think back to filtering, right? High pass filtering, if you set the filter cutoff at, let's say, 100 hertz, okay, it's going to high pass filter everything above. It's going to include everything above 100 hertz, but everything below 100 hertz will be reduced. And that's where a lot of noise often will be, or maybe 200 hertz or something like that. So high pass filtering is just an easy way to do active noise cancellation. And then there's some other techniques like phase canceling and different things. But so active noise cancellation is very advantageous for reducing low frequency energy. And they talk about feedback suppression. It's kind of like hearing aid stuff, right? When you send the signal out 180 degrees out of phase, it'll minimize or cancel that original signal. And so depending on types of noise, you could potentially do that. Acoustic pipe lagging, so when there's a lot of noise through the piping, you can put an inline silencer whenever you can't do, an inline silencer is essentially one of the best noise reducing techniques available, but when it's not possible to do that, you can use pipe lagging. And with pipe lagging, the exterior surface of the pipe is wrapped with this material, and you see that a good bit. Okay, you see a lot of places have this material, and so here you can see an example. You have a sound absorbent material around the pipe. This should look familiar. This is outside of Allen Hall, but there you can see some pipe lagging to reduce noise. So if you reduce this is about reducing the noise along the pathway to the worker. So, you know, the sound can either reach the worker directly or indirectly through reverberations. And so reflections from the walls, floors, ceilings can increase the sound levels, which we all know. One way to reduce this is through the use of acoustic enclosures, which in my experience can be pretty expensive. Sometimes it's just absolutely necessary depending on the work environment. But these can be quite expensive, and it has to have climate controls, right? It has to have heating and cooling depending. It has to have some kind of ventilation system. But they're effective, but they're very expensive. So that's my experience with acoustic enclosures. But they usually have some type of sound absorbent material, such as foam inside and heavy stiff materials on the outside. So you can purchase these from companies, you can build your own, but these are the considerations: the overall noise level and the octave band levels, how much attenuation you need, the size of the equipment and how much space you need, and then operational and maintenance requirements, including ventilation, lighting, HVAC, all of that stuff. So here is an acoustic enclosure. Again, that should look familiar. But you can see it's covering the base of that noise source outside of Allen Hall. Here are some common absorption coefficients by frequency. And so here you can see carpet. I mean, it does have some noise reduction coefficient. And essentially this describes the ability of the material to absorb sound. One of the best is the foam. Okay, polyester urethane foam. Thicker gives you a little bit more. If you spray it on, it's even better. So those are just some examples. And again, you won't, in your career, you're not going to have to be making decisions about this kind of thing. But it's important that if you work in this environment, you're familiar with this information. So when we talk about the use of shields or barriers between the noise and the workers, barriers are typically defined by what they call their transmission loss rating. And they measure that using 16 different frequencies from 125 to 4,000 hertz is pretty common to determine a barrier sound transmission class. So these are specific attributes that you look for. And I don't have a lot of experience like purchasing these or being involved. Again, this is something that usually we're not heavily involved in. But again, it's good to have this information. So isolating workers inside of a booth, that's super expensive. You don't see that very often, but it's something that you can do. So administrative controls for workers who are exposed to hazardous noise after the use of if they're still exposed after you do all these engineering controls, then one choice is to revise their work schedule to limit the duration or intensity, move them to different places. So this is more administrative, like HR type stuff, where you're going to be, when, and that sort of thing. So whenever you exhaust all of your engineering controls, then you have to start thinking about administrative controls. And again, here's these non-auditory effects, which were talked about in, I believe, Chapter 1. Cardiovascular dysfunction, breathing annoyance, sleep disturbances, which can cause fatigue, and that sort of thing. And other examples of negative effects of medium noise exposure, so not 90, 95 dB noise exposure, or long-term interference with sleep, relaxation, interference with sleep sleep recognition and communication. That should be speech. Interference with speech recognition and communication, and interference with tasks requiring a high degree of attention and communication. So just an overall kind of annoyance because of the sound. All right, that's it for Chapter 3, and we'll see you soon.